In this video, we'll be looking at examples of using the factor theorem to help us find the formulas for polynomial functions. Remember that the factor theorem tells us that if any number is a zero of a polynomial function, then x minus that number is a factor of that polynomial. Let's now take a look at some examples. In our example here, we want to find the formula of a degree 3 polynomial function with zeros -2, 1, and 3. The factor theorem tells us that because -2 is one of my zeros, we know that our function has a factor of x minus -2. And since 1 is one of the zeros of our function, we know that x minus 1 is one of the factors of the polynomial. And lastly, since 3 is one of the zeros, we know that x minus 3 is one of the factors. Putting all of this information together, we see that our function f of x should look like x minus -2, which we can write as x plus 2, times x minus 1 times x minus 3. And what we have here is a degree 3 polynomial, because if we were to multiply out the factors of x plus 2 times x minus 1 times x minus 3, the product of the x's in each of the factors gives me an x cubed, making this a degree 3 polynomial. Let's take a moment to look at the graph of this polynomial. To graph our function, we can graph the equation y equals, in parentheses, x plus 2 times x minus 1 times x minus 3. We see that our function does indeed have zeros or x-intercepts at -2, 1, and 3. We see on the graph we have the x-intercept here at -2, at 1, and at 3. However, this is not the only degree 3 polynomial that has these x-intercepts. If we think back to graph transformations, we learned that when we apply a vertical scale to a function, that will stretch or compress our graph vertically, which means that we take the points on our graph and we multiply the y-coordinate by some scaling factor. Now, at the x-intercepts -2, 1, and 3, the y-coordinates of those points are zeros. So no matter what vertical scale I apply, the locations of those points will not change because 0 times any number is still going to be 0. What this means is that vertical scales do not change the locations of x-intercepts. So for example, if we scale our function by 1/2, we see that we still have a degree 3 polynomial with x-intercepts at -2, 1, and 3. So it's a degree 3 polynomial with zeros -2, 1, and 3. So another option for answering our question is f of x equals 1/2 times x plus 2 times x minus 1 times x minus 3. But that's not all that we can do. We can scale it by another factor. For example, we can stretch it by a factor of 3. We still have a polynomial function that's degree 3, and the x-intercepts are still -2, 1, and 3. We can even do a vertical reflection, so multiply out in front by -1. We see here that we have a flipped version of our graph, but the x-intercepts are still at -2, 1, and 3. So no matter what vertical scale we apply, as long as we're not scaling by 0, we'll always end up with a degree 3 polynomial where our zeros are -2, 1, and 3. So in general, our formula for our function is going to be some vertical scale, which we call a, times the factors x plus 2 times x minus 1 times x minus 3. Next, let's add on an extra condition. What if we want our polynomial function to go through the point -1, 2? Let's go to our graph and add that point onto our graph. -1, 2. We see that at the moment, the function -1 times x plus 2 times x minus 1 times x minus 3 does not go through that point. But perhaps if we adjust the vertical scale, we'll eventually come across a polynomial that does go through that point. For example, what if we change the vertical scale to 1/2? We see that our polynomial still does not go through that point. So let's adjust it, maybe change our vertical scale to 1/3. My graph got closer to the point -1, 2, but still not quite there. What if we change the vertical scale to something like 1/5? Our graph gets close to the point -1, 2, but doesn't quite pass through that point. Now, it would be inefficient to just randomly try different numbers for our vertical scale and hope to find a function that goes through that point. Instead, what we're going to do is we're going to solve for that vertical scale directly. Remember that for a point to be on the graph of a function, we know that the x-coordinate is the input to the function and the y-coordinate is the output. So if our function goes through the point -1, 2, this means that f of -1 equals 2. When I input -1 into our function, the output is 2. Now, in general, a degree 3 polynomial that has our desired zeros is f of x equals a times x plus 2 times x minus 1 times x minus 3. So f of -1 would be a times -1 plus 2 times -1 minus 1 times -1 minus 3. So all we've done here is plug in -1 everywhere we had x. And what we want is that f of -1 is equal to 2. So I'm going to set this equal to 2. Now, what we have here is an equation with a as the only unknown quantity. So we can solve for a to figure out what vertical scale we need. Now, let's simplify this. On the left, we have a times -1 plus 2 is +1, -1 minus 1 is -2, and then lastly, -1 minus 3, that's -4. And this is equal to 2. On the left-hand side, a times 1 times -2 times -4 gives me 8a. And on the right-hand side, this is still equal to 2. So lastly, to get a by itself, we divide both sides by 8. We get a equals 2 divided by 8, which is 1/4. So what we've learned here is that if a is 1/4, then f of -1 would equal 2, meaning our function would pass through the point -1, 2. Let's check this on our graph. Let's change that vertical scale. Instead of 1/5, let's change it to 1/4. And we see here that our graph now passes through the point -1, 2. So if we want a degree 3 polynomial function with zeros -2, 1, 3, and we want the polynomial to go through the point -1, 2, its formula would be f of x equals 1/4 times x plus 2 times x minus 1 times x minus 3. Let's try working through another example. In this example, we want to find the formula of the degree 4 polynomial function with zeros -3, 0, 1, and 4 that goes through the point 2, 4. We know from the factor theorem that if -3 is a zero of our polynomial function, we know that our polynomial has a factor of x minus -3. If 0 is a zero of our function, then the polynomial has a factor of x minus 0. If 1 is a zero of our function, then the polynomial has a factor of x minus 1. And lastly, if 4 is a zero of our function, then we know that the polynomial has a factor of x minus 4. Putting all of that together, we know that our function will look like f of x equals x minus -3 times x minus 0 times x minus 1 times x minus 4. And what we have here is a degree 4 polynomial because we have a product of 4 of these factors, and multiplying out the x's in each of these factors will give me x to the 4th power. One last thing to remember is that applying a vertical scale will not change the location of the x-intercepts, so we can multiply out in front by a vertical scale a. So in general, our polynomial function will look something like this. Let's simplify this a little bit. We have f of x equals a times, instead of x minus -3, we can change that into an x plus 3. Instead of x minus 0, we don't really need to write the minus 0. This will just be times x. And then our next factor is x minus 1, and then x minus 4. So again, this is the general formula for a degree 4 polynomial with zeros -3, 0, 1, and 4. Let's take a look at the graph of this function to make sure that it does have our desired zeros or x-intercepts. Let's type in the equation for the graph of our function. We're going to have y equals, now for now we won't include the vertical scale, we'll adjust the value as we go. So we have our first factor, x plus 3 times x minus 1, and then lastly times x minus 4. So here we have our polynomial function, and we see that it does have our desired x-intercepts, -3, 0, 1, and 4. Again, what we've shown here does not have any vertical scale applied, but we can apply any vertical scale we want, and you'll see that the x-intercepts will not change locations. For example, if we apply the vertical scale 1/2, we still have a polynomial function with x-intercepts -3, 0, 1, and 4. We can also go to like 1/3 or 1/5 or 1/10. All of these vertical scales still give us a function with our desired x-intercepts -3, 0, 1, and 4. We can even apply a reflection, and you see that the locations of our zeros or our x-intercepts are still the same. So as long as our vertical scale a here is not equal to 0, we're going to have a degree 4 polynomial that has the zeros -3, 0, 1, and 4. So now let's focus on the part where we want our polynomial to go through the points 2, 4. Let's plot that point on our graph. The point 2, 4 would be over here. And we see that with our current vertical scale of -1/10, our polynomial does not pass through the point 2, 4. So our goal here is to find the exact value for our vertical scale a so that my graph goes through the point 2, 4. Now remember that the x-coordinate 2 is the input to the function, and the y-coordinate 4 is the output of our function. So if we want the graph of our function to go through the point 2, 4, we need f of 2 to equal 4. This statement here will allow us to set up an equation to solve for a. So let's begin by writing down what f of 2 is. So all we have to do is go to our function and replace all of the x's with 2's. So f of 2 would be a times 2 plus 3 times 2 times 2 minus 1 times 2 minus 4. And what we want is that this is equal to 4. So set this equal to 4. So now let's simplify this left-hand side here. We have a times 2 plus 3 gives us 5, then times 2, then 2 minus 1 gives us 1, and then lastly 2 minus 4 gives us -2. And we want this equal to 4. On the left-hand side, a times 5 times 2 times -2 gives us -20 times a. This is equal to 4. And then one last step to solve for a is to divide both sides by -20. So a is equal to 4 divided by -20, which simplifies to a equals -1/5. Let's go to our graph to confirm this. If we change the vertical scale to -1/5, we see now that our polynomial function does indeed go through the points 2, 4. So a degree 4 polynomial with zeros -3, 0, 1, and 4 that goes through the point 2, 4 has the formula f of x equals -1/5 times x plus 3 times x minus 1 times x minus 4. So in this video, we learned how to use the zeros of a polynomial function to help us find the formula for the function. In our next video, we'll learn a little bit more about the zeros of a function and talk about something called multiplicities.